Yes, hi everyone. Welcome back to Power Systems to Online series. I think now we are in the discussion of Corona. We are in the discussion of very important topic of Power Systems 2. One of the important topic of Power Systems 2, that is Corona. And today let us we discuss about the advantages and disadvantages of Corona, and later we discuss the dielectric strength of air and disruptive critical voltage. Okay, yeah, the first one is, what are the advantages and disadvantages of Corona? Keep reading. Advantages and disadvantages of Corona. Just tell me, what are the advantages and disadvantages? We know the disadvantages. Yes, we know disadvantages very well. That is, there is a definite loss of power, and there is a non-sinusoidal voltage drop due to non-sinusoidal corona current, and owing to the formation of corona, ozone gas is produced, which chemically reacts with the conductor and causes corrosion. Yes, these are the disadvantages of corona. Yes, so once again I will repeat all these disadvantages. Yeah, the first one is, there is a definite loss of power. Power losses occur. There is a definite loss of power. And the second one is, there is a non-sinusoidal voltage drop due to the non-sinusoidal corona current. Non-sinusoidal voltage drop due to the non-sinusoidal corona. And what is the problem with this? These may cause some interference with the neighboring communication circuits due to electromagnetic and electrostatic induction effects. Yes, that is the neighboring conductor. That means we may have the communication system. Communication system is also somewhat near to the electrical transmission system. So hence this may affect that system also. That is the non-sinusoidal voltage drop due to the non-sinusoidal corona current, and this may cause some interference with the neighboring communication circuits. Okay, due to electromagnetic and electrostatic induction effects. And the most important thing, the last one is, the owing to the formation of corona, ozone gas is produced. Ozone gas is produced. Yes, what is the problem with the ozone gas? The problem with the ozone gas is which chemically reacts with the conductor and causes corrosion. It's corrosion. It is CORROSION. Corrosion. Yeah, these are the disadvantages. Then is there any advantage we can expect from the corona? Yes, is there any advantage we can expect from corona? Yes. Now let us see advantages. Advantages of corona. Yeah, only two we can say. The first one is, on the formation of corona, the sheet of air surrounding the conductor become conductive, and there is a virtual increase in conductor diameter, and due to this virtual increase in conductor diameter, the maximum potential gradient or maximum electrostatic stress is reduced. Thus, probability of flashover is reduced and system performance is improved. That is, there is a probability. We cannot say exactly. The probability is the flashover is reduced and the system performance is improved. Yes, once again, I will repeat the same statement. On the formation of corona, the sheath of air surrounding the conductor become conductive, and there is a virtual increase in conductor diameter, and due to this, the virtual increase in conductor diameter, the maximum potential gradient or maximum electrostatic stress is reduced. Okay, Yes, why electrostatic stress is reduced? Due to virtual increase in conductor diameter. Due to virtual increase in conductor diameter. So simply we can say due to the corona, the virtual increase in conductor diameter is increased. Virtual increase in conductor diameter. And due to this, electrostatic stress is reduced or maximum potential gradient is reduced. So hence the probability of flashover is reduced and the system performance is increased or improved. So this you can say. And second one is effects of transients. Yeah. The second one is effects of transients produced by lightning and other causes are reduced. Since the charges induced on the line by lightning or other causes will be partially dissipated as a corona loss. Yes, we know that the corona loss in the sense it is in the form of the energy is dissipated in the form of light, heat, chemical action, etc. So if suppose the transients are produced due to the lightning, so due to the corona, what happened? The loss is produced as energy dissipated in the form of light. So this will be comes under the loss of the corona. So this is also one of the advantage. So in this way it acts as a safety valve, and sometimes lines have been purposefully designed to have an operating voltage near to the critical voltage in order to do away with necessary for and expense of light arrestor gear. Okay, an objection of this scheme is that the critical voltage is not fixed for a given line but may vary considerably with the changes in the weather. Okay, so these are the advantages of corona. Okay, yes, once again let me know what are the advantages of corona. Due to the corona, virtual increase in diameter of the conductor. Yes, this virtual increase in diameter of the conductor will increase the maximum potential gradient. We may have the maximum potential gradient of the conductor, or maximum electric stress is reduced. Maximum electric stress is reduced. So thus we may have the probability of flashover is reduced and the system performance is improved. And second one is, and we know that the transients are produced by lightning and other causes are reduced. Yes, because the corona loss is in the form of energy dissipated in the form of light or heat and chemical action, etc., like this. Okay. Yes, so now these are the advantages and disadvantages of corona. Now let us we discuss about dielectric strength of air and critical disruptive voltage. Keeps adding dielectric strength of air and critical and disruptive critical voltage. Disruptive critical voltage. That is dielectric strength of air and disruptive critical voltage. So let us we see these two. That means we have the two formulas. Let us we see those two formulas, and based on that we will solve some problems. Okay? Yeah. The value of potential gradient at which complete disruptive of air occurs is called disruptive strength or dielectric strength of air. Okay, the value of potential gradient at which complete disruption of air occurs. Complete disruption of air occurs is called the disruptive strength or dielectric strength of air. And the breakdown strength of air at a barometric pressure of 760 mm and the temperature of 25 degrees centigrade is 30 kilovolts per centimeter maximum. This is the maximum value. Yes, what is this? The breakdown strength of air, 30 kilovolts per centimeter. Maximum value is the breakdown strength of air. Breakdown strength of air. So when the pressure is 760 millimeters at room temperature, is normally 25 degrees centigrade, is 30 kilovolts per centigrade. In the problem, if they do not given any value for breakdown strength of air, usually we used to take as 30 kilovolts per centimeter. And moreover, this is maximum. Then what is RMS value? RMS value in the sense divided by maximum by root 2. 21.1 kilovolts per centimeter. This is RMS. 21.1 kilovolts per centimeter. It is RMS. Yes, what about these two? These two are breakdown strength of air. Breakdown strength of air at 760 mm of pressure and 25 degrees centigrade of temperature. So which is given by 30 kilovolts per centimeter maximum value and 21.1 kilovolts per centimeter RMS value. Okay, and the next one is, so here now we can denote the breakdown strength of air by G naught. G naught. So G naught stands for the breakdown strength of air. So which is 21.1 kilovolts per centimeter. This is RMS. And G naught is equal to 30 kilovolts per centimeter maximum. 30 kilovolts per mag. If we want to find the disruptive critical voltage in the form of maximum value, then we can take 30. In RMS, so we used to take 21.1 kilovolts per centimeter. Okay. Yes. The next one is the value of dielectric strength of air depends upon the density of air, and it is directly proportional to the density of air over a wide range and thus directly proportional to the barometric pressure and inversely proportional to the absolute temperature. Yes, this is G naught. That is G naught is the breakdown strength of air is directly proportional to the pressure and inversely proportional to the temperature. Thus, breakdown strength of air at a barometric pressure of B. So, initially we have taken that is 760 mm of pressure and 25 degrees centigrade of temperature. But here, generally, if we take it in the form of some variable values, then it will be as the breakdown strength of temperature, the breakdown strength of air at a barometric pressure of B centimeter, pressure of B centimeter, and mercury, B centimeter of mercury. Mercury, Hg stands for hafnium. Hafnium is mercury only. And temperature at T degree centigrade, small t degree centigrade. Yes, small t degree centigrade. So that we can consider delta into G naught. Delta into G naught. So this will be given by delta into G naught, where delta is where delta is B into 10 divided by 760 into 273 plus 25 degrees centigrade. This is temperature in kelvins. Temperature in kelvins. 273 plus T. Okay, so this can be given by 3.92B divided by 273 plus T. Yes, do you got this? Delta. This is the value of delta. Okay, next. Yes, if suppose in case of the parallel conductors, it has been shown that the maximum potential gradient occurs at the surface of the conductor and is given as, that is, G max is equal to V divided by R into ln d by R. Ln d by R. So this is in the case of parallel conductors, the maximum potential gradients occurs at the surface of the conductor. So that value is given by G max is equal to this value. Now what is R here, where R is the radius of the conductor in centimeters, radius of the conductor in centimeter, and D is the spacing of the conductors in centimeter. R is radius of conductor. In centimeter, and D is, yes, what is D? The spacing of conductors. I think you can remember these formulas from EMF. In the EMF also we have the same formulas. G stands for electric field intensity. Just you consider G as electric field intensity. Okay. Electric field intensity in terms of electric potential. Maximum electric field intensity. And what is V? V is the value of voltage of the conductor to neutral. Conductor to neutral. Both G max and V being expressed in RMS value. When the disruptive gradient of air is reached at the conductor surface, then when the disruptive gradient of air is reached at the conductor surface, then G naught is equal to V D naught divided by R into ln d by R. R into ln d by R. Or we can also say where V D naught is called disruptive critical voltage. disruptive critical voltage, which is given by VD naught is equal to G naught R ln d by R. Disruptive critical voltage is G naught R ln d by R. And we know G naught. G naught is 21.1 or 30 kilovolts per centimeter. 21.1 kilovolts per centimeter, that is the RMS value, and 30 kilovolts per centimeter is maximum value. Okay. Yes, generally that is the practical. The corrections have to be applied to the this formula for air density and the surface conditions of the conductor, and thus the complete formula becomes VD naught is equal to G naught delta M naught R ln d by R. So here we can observe there are two additional terms are there. So what are those? The first one is delta and second one is M naught. Already we have delta, we define delta. Delta is called air density factor. Delta is air density factor. Air density factor. Yes, air density factor. What is the formula for air density factor? 3.92 B divided by 273 plus T degree centigrade. Okay, and the value of M naught is the conductor surface condition factor. Generally, the M naught may be taken as unity, or it may be varies from 0.98 to 0.93 and 0.87 to 0.80 for polished and roughened of stranded conductors. That is, M naught is conductor surface condition factor. Yes, what is M naught? This is small m. M naught is conductor surface condition factor. So generally we can take M naught as 1 if they do not given any value, or for polished stranded conductors it is 0.98 or 0.93, 0.98 to 0.93, and this value may be 0.87 to 0.8 for rough stranded conductors. This is for polished, and this is for rough. So that is how we can take the value of value of conductor surface condition factor, and we have written the equation for VD naught. What is VD naught? VD naught is disruptive critical voltage. Disruptive critical voltage. How you define the disruptive critical voltage? It is defined as the minimum phase to neutral voltage at which corona occurs and holds good for fair weather conditions. As once again I will repeat, the critical disruptive voltage or disruptive critical voltage is defined as the minimum phase to neutral voltage at which the corona occurs and holds good for fair weather condition. Fair weather conditions. Okay, that means it may be reduced during the bad atmospheric conditions such as fog, sleet, and rain and snowstorms. And during these conditions, this value may be reduced. Yes, now you write one problem. Just write on the problem. A three-phase transmission line consists of 1 centimeter radius, 1 centimeter radius conductors spaced symmetrically symmetrically 4 meters apart. 4 meters apart. Dielectric strength of air is dielectric strength of air is 30 kilovolts per centimeter. Determine the line voltage. Determine the line voltage for commencing of corona. Yeah, this is the problem. That is, he has given the data. Yes, here if you observe, he has given the spacing between the conductors. What is spacing between the conductor? How much it is? D is spacing between the conductor, we assume as small d. D is equal to 4 meters, but we require all the values in centimeters only. So hence if you convert to the centimeters, it will be 400 centimeters. 400 centimeters. Okay, next what about the radius of conductor? Small r is equal to 1 centimeter, as given. Next, what about the dielectric strength of air? G naught is equal to 30 by root 2 kilovolts per centimeter, or you can also write 21.21 or 12. 21, I think so. Just should check. Kilovolts per centimeter. Now, what about the line voltage for commencing the corona? Line voltage in the sense already we have phase voltage, but we need to take the line voltage. So that is VD naught is equal to VD naught is equal to G naught R ln d by r. So here I did not consider the value of m and m naught and delta. The reason behind that is he did not given any pressure, that is B he did not given, and T is also he did not given. So directly I have taken this formula. But this is the phase voltage. This is phase. If we want to find the line voltage, that is VD naught, line voltage, line to line. So that is root 3 into VD naught. So hence this will be root 3 into G naught is 21.21, R is 1, and ln 400 by 1. Yes, how much this value? This value is approximately 220 kilovolts. 220 kilovolts. They should check the answer. Okay? Yes, I hope you got the answer. Next, let us do one more problem. Still time is there. We'll do one more problem. Let's write on that. A three-phase 220 kilovolts 50 Hz transmission line consists of 1.2 centimeters radius conductor spaced 2 meters at the corners of an equilateral triangle. Calculate disruptive critical voltage. Between the lines. Irregularity factor is 0.96. Irregularity factor is 0.96, and temperature is 20 degrees centigrade, and barometric pressure 72.2 centimeters of mercury. The dielectric strength of air is 21.1 kilovolts RMS per centimeter. 21.1 kilovolts per centimeter RMS value. Yes, here Our objective is to find disruptive critical voltage between the lines. Yes, here also the same formula we can impose, but here he has given the value of irregularity factor. It is to be taken into account, as well as he has given the value of barometric pressure along with the temperature. Hence you need to find out the air density factor. So then you can go for disruptive critical voltage. Yes. Yeah, first one, let us we find air density factor, that is delta. Yes, what is formula for delta? Delta is equal to 3.92 B divided by 273 plus T. Okay, now you substitute B as 72.2 and T as 20 degrees. Then what is this answer? The value of delta is 0.966 approximately. Just should check all these values. If it is not correct, so you can go with the correct answer, correct values. Next, now we know the disruptive critical voltage to neutral, that is line to neutral or phase voltage, which is given by VD naught. VD naught is equal to VD naught is equal to G naught delta M naught R ln D by R. They should take ln value, not log. Ln stands for log base E. Okay, ln value as it is. Okay, now you substitute G naught, that is 21.1 delta 0.966 and M naught, that is M naught in the sense irregularity factor. Irregularity factor he has given as 0.96 and radius is 1.2 into ln, spacing is 2 meters. 2 meters in the sense we convert to the centimeters, it is 200 divided by 1.2. Then how much this value? How much this value? It is approximately 120.1 kilovolts RMS. 120.1 kilovolts RMS. But he asked to find the disruptive critical voltage from line to line. Disruptive critical voltage from line to line, that is root 3 into VD naught, which is given by, plus VD naught is 120.1 into root 3, that will be 208 kilovolts. 208 kilovolts. So this is also RMS value. Generally we used to find the value in RMS only. Okay. Yes, thank you for listening this class. Thank you for attending the class. Yes, I hope.
Thank you, Jesus. Thank you, Jesus.